All right, so it's possible that you already know one of the very important properties that a triangle has. But what we're going to do here is actually prove that property. So if you already know that the angles, the interior angles of a triangle have a sum of 180, this is going to explain to you how it is we know that, and we can prove that that's the case. If you didn't know that, we're going to prove that here. And we're going to do that using this diagram over here. So we have a triangle, no specific type of triangle. It's got 3 sides, 3 angles. And then we've got this line across the top of the triangle that intersects with the corner of the triangle at angle 1. And we're told that that line is parallel to the bottom edge of the triangle. So I know that this line here and the bottom edge of the triangle are parallel to each other. And that information there is enough for us to reach the conclusion that the measure of angle 1 here plus the measure of angle 2 there is plus the measure of angle 3 there is going to have to equal 180. So I'm going to set up my 2-column proof here and then we'll get started. All right, so I filled in my first given statement. Now, we know a lot about how parallel lines can create angle pairs that have some unique properties. So we've been talking a lot in our most recent lessons about same side interior angles, alternate interior angles, corresponding angles, all those different groups. And we're going to notice some here. So if this bottom edge of the triangle is parallel to that line up there, well, that means that I have 2 different transversals that I could imagine intersecting those 2 parallel lines. I've got one there, which is going to create alternate interior angles. And I've got one here, which is going to do the same thing. So in 2 separate statements, I'm going to talk about how I know that those pairs of angles are congruent to each other. And I should actually use 2 arcs here because I don't know that those angles have the same measure as angles 2 and 4 do. So what I'm going to do is I'm going to claim that angle 2 is congruent to angle 4. And the reason that I know that that's the case is if parallel lines are cut by a transversal, which is what we have here, then alternate interior angles are going to be congruent. Okay, so this is helping. I now can definitively say that those 2 angles are congruent. Now I'm going to make an identical claim here with 3 and 5. I'm going to say that angle 3 is congruent to angle 5. For the same exact reason. All right. So how is that actually going to help me here? Well, eventually I want to start discussing measurements. And I'm just talking about congruence here. So my next statement is going to shift from a conversation about congruence to a conversation about measurements. And this can all be done in one statement here. So I'm going to say that the measure of angle 2 has to be equal to the measure of angle 4. And at the same time, the measure of angle 3 has to be equal to the measure of angle 5, and that's because of the definition of congruence. The definition of congruent angles. Now we're really close. So I know that this angle here has the same measurement as that angle there. And I know that this angle here has the same measurement as that angle there. So now let's shift and discuss these 3 angles up at the top. Well, what do I have to know, or what do I know is true of those 3 angles? We've talked a lot about linear pairs in some situations where you'll see a line, and on that line we have 2 angles. And we've called those a linear pair before. What we've actually got here is a very similar situation, but instead of a pair of angles, we have 3 angles. So I'm going to refer to this as a linear triplet. All right. So I've got 3 angles that are creating a line. So what I'm going to say here is that if I add the measurements of angle 4, angle 1, and angle 5 together, that's going to equal 180. And I know that because this is a linear triple, or these 3 angles are linear triplets, and linear triplets are supplementary. So that's not something that we've really talked a lot about. It's not a situation that's going to come up very often, but that is a reason we can use here. And so finally, I'm going to make a substitution. I know that the measure of angle 4 is the same as the measure of angle 2. So I'm just going to replace that with a measure of angle 2. And I know that the measure of angle 5 is the same as the measure of angle 3. So I can claim that this equation would also hold true. And my reason for that, I don't want to write it there. My reason would be the substitution property of equality. And that's what goes in that spot there. And the reason I don't want to write that is I am going to end up writing something here, here, and here. So that's the end of my proof. And that leads to a really important theorem, which we call the Triangle Sum Theorem. So we should probably make a note of that Triangle Sum Theorem. So what the Triangle Sum Theorem says is what we just proved to be true. The sum of the interior angles of a triangle, any triangle, is 180 degrees. Good. So I said any triangle because there are a lot of different types of triangles, but as long as you've got 3 sides and 3 angles, 3 interior angles, it's a triangle, and those interior angles add up to 180 degrees, which is what we just proved. I'm not going to ask you to prove this on your own, but now that we know this, we can use that information to help us. So before we start dealing with calculations involving those angles, I think it's important to discuss the different types of triangles that exist. So what we can do is we can choose to look at a triangle in terms of its side lengths. And there are 3 ways we can sort of break this down. We have triangles that are scalene, which are going to be triangles where no sides or angles are congruent. We have isosceles triangles, and this is a case where we have at least 2 congruent sides. With that would come 2 or more congruent angles. And then finally we have equilateral, which is where all 3 sides, and with that would come 3 congruent angles as well. Now, if we choose to approach the classification of a triangle from the perspective of the angles, well, then we can say that we have acute triangles, which are triangles that have all of its angles less than 90. We have what we can call equiangular triangles, which is sort of a hard thing to say, but if we have all angles congruent. We can have right triangles, which would be triangles containing one 90-degree angle. And then we have obtuse triangles, where one angle is greater than 90 degrees. So these are all the ways that we can classify triangles, and what we're going to do here is draw in what any combination of these angular and side classifications would look like in a triangle. So what I'm going to do here is I'm going to draw all of the triangles that go into these boxes, and then we'll go through the labels together. Okay, so the first triangle that I want to talk about is this acute scalene triangle, where all the angles have to be less than 90 degrees, and also all the sides have to be of different lengths. So that's what we're seeing here, right? We have a 50-degree angle, a 60-degree angle, a 70-degree angle. If you add these together, you will get 180 degrees, but you'll notice none of the angles have the same measure, and all of these sides have been marked to indicate that they wouldn't have the same measure. Now, if we take a look at the triangle to the right, which would be the isosceles acute triangle, it still has all angles less than 90 degrees, but now I'm going to indicate that 2 of my sides have the same length. With that is actually going to come 2 congruent angles as well. So again, you'll see that all of the angles are less than 90. None of these are greater than a right angle or equal to a right angle. And we have 2 sides that have the same measure, so it is isosceles. Over here in our equilateral acute triangle, I'm going to indicate that all of these angles have the same measure, and all of the sides have the same measure. So the key there is creating a triangle where all 3 sides are congruent. When you do that, though, you're going to create 3 angles that all have the same measure. And if you take 180 and divide it by 3, that's going to mean that each of these angles has a measure of 60 degrees, which is less than 90. Now this box here is blank, and the reason for that is because you cannot create a scalene triangle where all of the angles have the same measure. It can't be done. So this is not possible. Right? Scalene means none of the sides are congruent. But the minute you make those sides a little bit different, you're going to change the angles. So I'm not going to be able to, for example, start with a triangle like this, which is equiangular, and then adjust one of the sides to make it scalene while keeping all of the other angles the same. You can't do that. So it isn't possible. But I do have two other equiangular triangles that I can draw in. This triangle here is equiangular and ends up looking exactly like the equilateral triangle that we drew in the previous diagram, because all of these angles are 60 degrees again. And you'll notice that it's still isosceles because we need two or more congruent sides for it to be isosceles. And here we have 3 congruent sides, so it still counts. The equilateral, equiangular triangle also looks exactly like those previous 2 triangles, which means that these 3 triangles are the same triangle. So if you're looking at that triangle, there are 3 different ways to classify it. You could call it equilateral acute, you could call it equiangular, isosceles, a lot of different ways to describe a perfect equilateral triangle, but usually we use the term equilateral. These triangles all have to be right triangles, so I'm just going to indicate that they are by putting that little box. We've got a right angle there. But in this triangle here, it has to be scalene, so all of these sides have to have different lengths. So I'm just going to indicate that each of these sides has a different length. And none of those angles would have the same measure either. I could imagine this being a 30-degree angle and this being a 60-degree angle so that it adds up to 90. The other triangle here, which is right, is isosceles. So in that situation, I need to show that 2 of my sides have the same measure, and with that is going to come opposite angles with the same measure. This is another triangle that can't be done, because the minute one of your angles is 90 degrees, all of your angles can't be 60 degrees anymore. And then our bottom row is obtuse triangles, which means we have to have one angle that's greater than 90 degrees. So in a case where we want all the sides to be different, I'm just going to maybe label these. So we'll call this 120 degrees, and we'll put a 20-degree angle over here, looks like, and then this would have to be 40 degrees for it to add up to 180. And so that's going to create a bunch of different side lengths as well. But over here, it's isosceles and obtuse. So I'm going to indicate that these 2 sides have the same length and that these angles are the same, but we'll say that this is a 130-degree angle there, showing that it is obtuse. And again, we have a situation that's not possible, because I can't have all 60-degree angles if one of them is greater than 90 degrees. All right, so that's just a basic introduction to some triangle properties, and we'll continue on with this on Monday.